Good afternoon. Thank you, Nicolas, for the introduction. Thank you all for being here. It's really a pleasure to be here. I want to thank the organizers, of course, for the invitation. So I was here, I came a few times as a postdoc. It was about 10 years ago, a little bit more. It was always really a great pleasure, and I learned a lot, and I was just entering this community of waves in complex media at the time, so it was really important for me, and also I met a few exceptional people. So today I will tell you about correlated disorder in photonics. It's a topic that emerged about 15 years ago, I would say, that grew quite considerably. And recently, with a great team of colleagues, we wrote a thorough review article on the topic that is covering theoretical and experimental aspects that you will find here. So the content of this talk will mainly be contained also in this article, clearly with more details. I will not cover all aspects, of course, and you've seen yesterday already a talk by Geoffroy Aubry on a related topic with hyper-uniform structures and localization. I will not talk about that. And since this is a school, I will try to take a step back and go into more fundamental and basic concepts. In particular, I want to tell you about a theory that can explain how correlated disorder can impact the scattering, transport, and localization of light in matter. And I will tell you a little bit also about the novel optical functionalities that could be used using engineered disorder. So let me start with a few examples of the structures that we are interested in that cover about 15 or almost 20 years of research. All of those structures were created by men and women. So, and they, yes, it is important. And they have very special optical properties that rely not only on the scattering properties of individual scattering elements, but also on their spatial arrangement. So here you have an example of what is known as a photonic glass. It's a dense random assembly of particles, spherical, that have almost all the same size. And here the scattering properties of those systems is inherited from the mere resonances of the particle. And because the system is very dense, there is a strong structural correlations that plays a role also. Here, this is an example from the group of Frank Sheffold in Fribourg, Switzerland. This is a three-dimensional hyper-uniform structure that is expected to exhibit a photonic band gap despite the lack of periodicity in the structure. Here, this is a fractal disordered structure, which is called the Levy glass. It was made by the group where I did my postdoc in Florence about 10 years ago. This is essentially made by incorporating a broad distribution in size of glass spheres into a polymer matrix that contains nanoparticles. And this large-scale heterogeneity allows you to control the diffusive or super diffusive nature of transport. And at the bottom, you have a few examples of planar structures that people nowadays would call disordered metasurfaces, where the optical properties are due to first the scattering properties of the individual elements. So it can be a hole in a membrane, it can be a metallic nanocube or a high-index cylinder. Those particles, those scattering elements interact also with the surrounding layers and the interfaces that can have some strong effect, as in this case. And also the spatial arrangement of the scattering elements is creating a very sharp spectral and angular response. That can be interesting for light trapping in photovoltaics, for instance, light extraction in light-emitting devices, sensing, and other applications. So the first question is, what is correlated disorder? And more precisely, how do we quantify correlated disorder? So as you know, the scattering of light is produced by spatial variations or fluctuations of the permittivity in space. Here, the permittivity is written as epsilon. It depends on the position, and you can decompose it into a background permittivity that doesn't need to be the permittivity of the host medium, but I will come back to this point, and a fluctuating part that depends on space. There are two types of disorder models that you could consider. The first one that you have seen already, for instance, in the talk of Nicolas Cheroret, it's a medium where you have a continuous permittivity that fluctuates in space. So in this case, you could define this background permittivity where you want in the system, and this, as we will see, is an important parameter. In this case, the correlation is a correlation of the permittivity in 2 points, and this is described by this total correlation function in points R and R prime, where the average, the ensemble average, denoted by the angular brackets, is made in 2 different points on the fluctuating part of the permittivity. The other type of disorder model is a particulate or discrete medium. So, for instance, an assembly of particles. And in particular, when the particles are all the same, all identical, you don't need actually to have this permittivity correlation function, but you can just take, for instance, the center of the spheres and establish a 2-point correlation function that is very simple to describe theoretically. It's a sum over the n particles in your system that can go to infinity, if you'd like, and these are the Dirac delta functions that indicate the position of the different particles in space. Rho here is the particle density in your system. So this is the quantity that is well known, it's the pair correlation function. Of course, in reality, you have also higher order correlations in your system. But the fact is that in optics and photonics, people have not looked in detail at the impact of higher order correlations on light scattering. So I will not discuss this point, and we will remain focused on the 2-point correlation. So let me give you a practical example. It's a fluid of hard disks. It's in 2 dimensions. And here, this kind of structure can be generated with a so-called Lubachevsky-Stillinger algorithm. The idea of this algorithm is that you take a box, you throw a certain number of points at random positions initially. The system has a certain temperature, so the particles can move. They have a hard surface, so they do not penetrate, they collide. And as you increase the size of the particles when they move, you start increasing also the packing density, the packing fraction of your system. And as you increase the packing fraction, you start having some short-range correlations that appear. And of course, if you go to a high filling fraction or packing fraction, you will converge to a periodic packing. Okay? So you can go all the way from a fully disordered system to a short-range correlated system. You can have a transition to a polycrystalline system and to the crystalline system. If now we analyze this kind of structure with the correlation functions that I was describing before, so on the permittivity here, what you will have for 2 different packing fractions, so a low correlation and a high correlation, is essentially that you have the correlation function starting at 2, decaying rapidly. This is a signature of the fact that you have a finite size in the particle. And then the decrease is exhibiting some oscillation at some point, and that depends on the kind of correlation that you have. So here, for instance, you know that the typical distance between 2 particles will be around here, typically. You can also, from this system, generate the inverted structure using, for instance, Voronoi tessellation. And here you can do exactly the same analysis. And you will see a very similar pattern. So actually, when you look at those curves, here it's very difficult, while by eye, you clearly see a difference between those two. Looking just at the correlation function, it's difficult to see any difference. So this is not, I would say, in terms of optical properties, not necessarily a very good descriptor of the correlation. Or at least you would need higher order correlations to describe those systems exactly. But since we have a mono-dispersed assembly of particles, you can look at the 2-point correlation function. And in this case, you have a very clear signature of the correlations. If you have a weak correlations, essentially you just have 0 because the particles do not penetrate each other on a certain, on the diameter, actually. And then it goes rapidly to 1. And when you have a strong correlation, you have this peak that arrives and then some oscillations at certain distance that decay as function of distance. This is very classical, and it has been well known, of course, for a long time. So how do such structures now respond to a wave excitation? Let me do a bit of history before that, because it's always good to go back in time a little bit. We think that we are doing always original things, but actually not always. So the story about scattering started essentially with the first works in the 19th century on the refractive index of fluids, of atoms and molecules, with key contributions from Mossotti, Clausius, Lorentz, and Lorentz, that gave rise to the rules that we know, Clausius, Mossotti, and Lorentz. At the beginning of the 20th century, there was some important works also from Rayleigh, who described by a clear formalism on small particles the blue color of the sky. This is Rayleigh scattering. Maxwell Garnett, that was trying to explain the color of metallic glasses, and me, that developed a rigorous solution of Maxwell's equations in the case of the scattering of an electromagnetic wave by a spherical particle. This is known nowadays as Mie theory. Now, the impact of the fluctuations on scattering was actually introduced thanks to a beautiful experiment on critical opalescence in binary fluids. I don't know if you have seen such an example already, but you can find some videos easily on the internet. Essentially, you have a mixture of two fluids, that the mixture is completely transparent at some temperature, and as you increase the temperature, you experience a phase transition of second order, and at the phase transition, you have this mixture of solution that becomes completely opaque, like milk. And actually, what was shown in particular by Einstein in 1910 is the fact that the scattering here is produced by those large density fluctuations that occur at the phase transition. So actually, the quantitative predictions of the scattering cross-section or scattering length were, in the works of Einstein and of Rayleigh, exactly the same, although the initial model was not the same. And we will see in the presentation that actually it makes sense to have the same quantitative results, and I will explain why. Then you have the theory, multiple scattering theory by particulate media, that was developed for a few decades. So there are the multiple scattering equations that people call often the Foldy-Lax equations, but actually those equations were already used by Kirkwood and Yvon about a decade before. And then, in terms of structural correlation, there is the popular example of the transparency of the cornea that was not explained because you have fibrils that should scatter light, and the transparency was already explained at this time as a result from the short-range correlations in the organization of those fibrils. And finally, in the 80s, started the study of mesoscopic phenomena with light, and this has been discussed quite a lot already in this school. I will not come back to that, but this includes Anderson localization, random lasing, weak localization before that, and so on. So the impact of structural correlations, of course, was known in a way, but let's say that the impact of correlations on light transport in diffusive media was not studied really or considered before this work from Froden and Maret. It was in 1990. And essentially, so this paper was presented yesterday already by Geoffroy. But the key idea is that the transport mean free path, which depends essentially on the form factor usually, so on the scattering cross-section of one particle, should be corrected with a structure factor to be correct, and the experiments and the theory are in very good agreement in this system. This is not very surprising, and those of you who know about X-ray diffraction or neutron diffraction, of course, recognize this formula very well. But this was still an important contribution, and also I want to say that there was a second paper that was published 1 week later, and that is not well known, that was actually discussing exactly the same results. Now that was about understanding how correlations impact light transport, but the idea of engineering disorder to control the transport parameters in scattering media was introduced only 15 years later by the group of Frank Sheffield with Juanjo Sáenz. And here, essentially, what is shown is that when you can control the separation between the particles in a solution, actually, you increase the short-range correlations in your system, and instead of having just a behavior where the transport mean free path increases, this is the inverse, increases with the volume fraction compared to the uncorrelated system, you can actually have some frequencies at which you will have a strong decrease of the transport mean free path, so potentially that could have been interesting for Anderson localization, although it's not sufficient to observe it. But anyway, this was the first, or probably one of the first at least, works where the proposition was to engineer disorder to manipulate the transport properties. And then a few years later, there was a series of works where this concept of engineering disorder was exploited. I told you already about very heterogeneous systems. That's a work that was coming from the group of Diederik Wiersma at Lens in Florence. There was some work from the group of Claudio Conti on the localization of light in periodic systems with some small structural imperfections, where it was shown that an optimal degree of disorder enables a stronger light localization. And also there was the very surprising observation at the time that you could have photonic gaps in disordered systems with short-range correlation. So for instance, in this amorphous diamond structure or in hyper-uniform structures. And that again was very surprising to the community because people who have worked on photonic crystals for years and looking at Bloch waves and so on were extremely surprised to have a band gap still in a disordered system. So let me give a short outline of this talk. I will start with a very simple introduction on basic theoretical concepts in multiple light scattering. This is not difficult. I mean, all of this is anyway not very difficult. I will try to highlight the important concepts that you should keep in mind. Then I will describe the extension of waves within the weak and strong fluctuation theories. I will discuss then the impact of negative and positive structural correlations on the optical properties of the systems, and I will conclude, if I have time, but I will conclude. I will have time. Okay. So let me start with this example. It's a numerical simulation in 2D. It's very simple, coupled dipoles. You have an assembly of 200 particles distributed randomly that you illuminate by a plane wave here. The result of that, here you have the field and here the intensity. It's a speckle pattern, of course. If you shape the wavefront, for instance, you can focus behind the material, and you can do a lot of very exciting things. But what we're interested in here is in the statistical properties of this scattered light. So if you decompose the scattered field into its average and a fluctuating part, so here the total field is the sum of the background field plus the scattered field. And the scattered field, you write it as the average scattered field plus a fluctuating part. That depends on the realization. Then you end up, when you look at the average intensity, into a decomposition in two parts, a ballistic or coherent intensity and a diffuse or also called incoherent intensity. That depends on the fluctuations of the field. So now if you do an average numerically of our 200 realizations, you can make this decomposition. You see that the speckle almost disappeared. You still have some diffraction, which is normal because the system is of finite size. The ballistic component describes the extension of waves in the medium, and this is exactly the Bouguer-Beer-Lambert's law in the system. I've been very careful. The extension, of course, is due to scattering and potentially to absorption, although in the rest of the presentation we will assume that there is no absorption. But in general, extinction is scattering plus absorption. And the diffuse part describes the scattering and the transport mean free path in the system. The scattering mean free path is the average distance between two scattering events, and the transport mean free path is the distance you need to make for light to be nearly isotropic in the system. So here I will focus on the extinction. So let me start for the theory with the very basics. We start with Maxwell's equations, and we can write very easily a vector wave propagation equation in the background field as a reference medium. And the term that creates the scattering, the source term here, is an effective scattering potential. That is essentially the susceptibility or an effective susceptibility. This is the fluctuation, delta epsilon, of the permittivity in space. So now we take the average of this quantity. So I just need to average this quantity, and the average here has to take the scattering potential and the total field, because those two quantities are not uncorrelated. They depend on each other, so you cannot separate them. And then you introduce a quantity, an operator that is very important. It's called the self-energy or the mass operator, which essentially expresses this quantity, this term here, as an integral of the self-energy, which is this operator, times the average field. The self-energy, it's a non-local quantity, and in general, it can be associated to a non-local effective permittivity tensor in your system that contains all the multiple scattering information in the medium. So essentially, the average field propagates as in a homogeneous medium with a permittivity that is the effective permittivity in the system, which is exactly what I've shown on the previous slide. Now, to define the extinction mean free path, you can simply seek for transverse solutions of the propagation equation of this form if you assume that you have an infinite medium. So this is simply a plane wave in the effective medium. And if you insert this solution in the wave equation that I've shown before and assume statistically isotropic medium, you end up with a transcendental equation where you have the effective wave number in the medium that is expressed in terms of the transverse component of the self-energy evaluated at this effective wave number. And the definition of the extinction mean free path is essentially that this is the inverse of the imaginary part of this wave number, this effective wave number. In the weak extinction regime, that is essentially when the extinction mean free path is much larger than the wavelength in the effective medium, then you end up with a simple relation for the extinction mean free path that is expressed as a function of the imaginary part of the transverse component of the self-energy, evaluated at the value of the wave number in the real part of the effective wave number. So again, if you say that your system is non-absorbing, then the extinction is the scattering. And that means that the problem of light scattering can be apprehended by determining simply the transverse component of the self-energy of the scattering medium. And this will be the point of the theoretical approach. So in the multiple scattering problem, usually you rely on green tensors, dyadic Green's functions. There are solutions of the propagation equation in the background medium with a point source. And that allows you to write the scattered field as an integral with the Green's function, that's the scattering potential and the total field. So if you write it in an operator form, this takes this very simple form here. But the difficulty is the fact that you have the total field here and the total field here. So to facilitate things, you introduce a quantity that is a transition operator, and that allows you to relate the total field only from the background field. And this transition operator contains all the scattering events in your system. So this is one scattering event, this is two scattering events, and so on and so on. If you do similarly for the average field, of course you get an expression that is known as Dyson equation, where you have the self-energy there. And you can, by exploiting those different formulas, express the self-energy in terms of the average of the transition operator, or if you express the transition operator in terms of the scattering potential, in terms of the scattering potential. So the self-energy here in this expression is expressed in terms of the permittivity fluctuations that interact together via the Green's function in your system, in the background medium. That's very classical. Now let's try to get some solutions and to find the impact of correlation. If you have weak permittivity fluctuations, you can define, you can say that the self-energy, you can expand it around the average permittivity fluctuation. And that gives you this expansion. And then you need to define a value for the background permittivity. You need to choose this value here. And the natural choice is to take the average permittivity. Okay? Why not? And if you assume that you have a statistically homogeneous and isotropic medium with a certain statistics, this is the correlation function I was presenting on the first slide. Then, after a few steps, you end up with an expression for the extinction mean free path that is expressed as function of the amplitude of the fluctuation. That's essentially this quantity, and an integral that involves the correlation function there. That's a correlation function of the permittivity here. The function P here is essentially the form factor of a small perturbation. In Rayleigh scattering, this is what gives the donut shape for the scattered power, for instance. And this depends on the polarization. And the scattering wave vector, this is very important. Q is defined for the wave number in the average medium. That is defined by epsilon b there. So the integral there is between 0 and twice the average wave number, or the wave number in the average medium. So in the end, that tells you already that spatial correlations are as important as the amplitude of the fluctuations for light scattering. And it is the wave number in the background or average medium that matters. That's the simplest model. Of course, here we assume that we have very weak permittivity fluctuations. So there is another approach that is very important. It's called the strong fluctuation theory. I will not describe it in detail, but just give you a few elements to understand how it works. Essentially, you describe your scattering medium by an assembly of infinitely small volume elements with a constant susceptibility, or a constant delta epsilon. This is the same physical viewpoint as the discrete dipole approximation. This discretization allows you to handle the singularity of the Green's function. You can separate the Green's function in two terms. A first term that is the non-local Green's function that describes the propagation from between 2 points, and a Green's function that contains the singularity. The fact that you handle the singularity allows you to define the local transition operator, that is essentially the polarizability of a small volume element here, and to formulate the problem and make a perturbative expansion on the self-energy for the exciting field and not for the total field. The exciting field is a field that is perceived by one small volume element due to the background field and the field radiated by all the other volume elements. This is really like the discrete dipole approximation. And when you do that, you can obtain some expressions as well that we derive here in the long wavelength limit. I'm considering a two-component medium for simplicity with permittivities epsilon p and epsilon h at two filling fractions. And then again, you need to choose a value for epsilon b, for the background medium. As a first step, you can take epsilon b such that the average of this local transition operator is equal to 0. Okay? And that leads to an expression that is exactly similar, exactly the same as before, except for the wave number here, which is actually defined from an effective permittivity that is given by the Brugman mixing rule. For those of you who know Brugman, this is exactly this expression. Brugman arrives directly by setting epsilon b such that the average polarizability, if you want, is equal to 0. You can make another choice and take the host permittivity as the background medium, and this leads to exactly the same expression with some subtle differences, except that the wave number here is the one given by Maxwell-Garnett. So usually people that know Brugman and Maxwell-Garnett consider that they come from two different approaches. And here we have actually a unique theoretical framework where the only parameter that we change is this background permittivity that leads to those two expressions. And the functional form of the extinction mean-free path is exactly the same, in the sense that you have a correlation function here, which is on the polarizability, not on the permittivity. And the difference is how you define the effective medium in your system. So in a way, the relation for the extinction between the structural correlations and the extinction, is defined regardless of the effective medium approach. It's only a matter of choosing the proper epsilon b. With this approach, you can make a similar treatment for point media. I will not describe everything, but this time we this time we rely on the two-point correlation function, and we end up with a formula that is the formula you've seen before, except for the prefactors, with the form factor and the structure factor in your system. The main difference with what has been done in the original article of Maret is that this wave number is obtained rigorously, and this is the effective wave number that is in the Maxwell-Garnett expression that was on the previous slide. And the same expression is obtained if you make the theory for the average intensity using Bit-Salpeter equation, only assuming that an effective index can be defined. So actually, you don't need an explicit model for the effective medium for this expression to hold, which is probably the reason why it is so robust in a way to scattering. So here I just want to summarize the different expressions that we have. We have seen that for fluctuating permittivity media, whatever the model that you use for the effective medium or the weak or the strong fluctuation theory, you get the same expression. We derive the same for the transport mean-free path, which is a slightly different expression, and the same for monodispersed particulate media. So this establishes really a fundamental relation between the structural correlations and the scattering of light. That is, again, independent of the choice of the effective medium approximation, which is a different problem. And it's interesting also because we obtained two results for Maxwell-Garnett, for particles and also for permittivity fluctuations. And actually, you have an equivalence that is rigorous in the limit of small particles, namely that for a fluid of small identical particles with a fluctuating density, the correlation of the fluctuation of the density here is equivalent to a fluctuation of the local polarizability in a continuous medium with fluctuating permittivity. And this is the reason why the results of Einstein and Rayleigh were exactly the same, actually, although they were using different approaches. So now let me move to a description of the correlated disorder and how this will impact scattering. So we can start from an uncorrelated system. Here I take a box, I throw randomly a certain number of particles, and as was shown by Geoffroy yesterday also, you can describe the correlations in a way using a fluctuation parameter for the number of points that is contained in the spherical window. So essentially, this was a relation that was already established by Ornstein and Zernick in 1914 with some subtle differences, and that was refined and so on by different authors, eventually by Torquato and Stiligan in 2003. And essentially, that means that the fluctuation in the number of points that you have in a window, in a limit where the size of this spherical window is going to infinity, is equal to the limit of the structure factor when Q, the wave number, goes to 0. So by looking at the structure factor close to Q equal to 0, you get some information on the fluctuations in the number of points. And this relation also gives you something directly related to the total correlation function H2 with this integral. And from this relation, it's interesting because you can define two classes of disordered media, correlated disordered media. One with negative correlation, when this quantity is negative, that corresponds to sub-Poissonian fluctuations. And that, in practice, means that the particles try to repel themselves. These are some kind of short-range correlations. And you can also have positive correlations where this quantity is positive, which means that the structure factor close to 0 will be larger than 1. That corresponds to super-Poissonian fluctuations, and that leads to structures that are more aggregated, forming sometimes some fractal patterns. So in this class of negatively correlated disordered media, there are different families as well. You can have short-range correlated, polycrystalline, imperfect ordered, disordered hyperuniform, and stealthy hyperuniform. Here I'm showing the pair correlation function that correspond to all those systems. You see that the pair correlation always exhibits some kind of oscillations, and the structure factor close to 0 is always smaller than 1, or even equal to 0 on a certain range. Most studies in disorder engineering in photonics are considering this kind of negative correlations, actually, because they produce more interference, more interesting spectral and angular response as well. And this is very easy to understand if you take the structure factor for a fluid of hard particles. Again, as you increase the packing density, you have the structure factor that goes to 0, approaches 0 in the long wavelengths at most frequencies, and exhibits a peak that decays. If you represent that in terms of frequency and scattering angle, that means that at long wavelengths, small frequencies, you will have a suppressed scattering. And that's the reason why you have transparency. And at some frequencies that correspond actually to the Bragg resonance in periodic media, you have some enhanced backscattering. The result on that is very clear, is that when you have a dense assembly of particles that are strongly correlated, you can have a very strong transparency, and there is a very nice work with a solid, rigorous theoretical formalism that was developed by our colleagues at Institut Langevin on the topic. And when you tune the structural correlations such that they are comparable to the wavelengths, you have certain wavelengths that will be reflected more efficiently, and that explains many structural colors that are observed in the natural world nowadays, in birds, insects, mammals, even. I just want to do a parenthesis on these structural colors because recently, with my former group in Bordeaux, we thought of studying the visual appearance or the potential of disordered metasurfaces or surfaces, nanostructured surfaces, to control the visual appearance of an object. That's actually motivated by a very strong interest from the industry. The industry is very interested in designing the visual appearance, essentially, so to have some predictive tools to predict how an object in reality will look like. But there was no method today to have some predictive predictions of the appearance, except from the color. But the color is not making the appearance of an object. It's much more complicated than that. And what we did in a recent work was to develop a platform, a numerical platform that is mixing some theoretical concept of multiple scattering and computer graphics to predict the visual appearance of macroscopic objects in realistic environments. So these are some quantitative predictions of the visual appearance in a computer. So I'm showing here just an example to illustrate the impact of structural correlations. So imagine you have an object, a spherical object like that, which is covered by a random assembly of silver particles of a certain size that are deposited on glass at 10% filling fraction. The object is illuminated by a small window here that you can see in specular reflection. So the appearance is very gray, it's not very interesting. But as you increase the structural correlation in a system, you have some kind of rainbow-like colors that appear, which is essentially due to the structure factor of your system. You can see that around the specular direction, you have a clear suppression of the diffuse intensity, and at larger angles, you start having a large intensity that depends on the wavelength, so this creates some nice colors. So we did actually much more than that in the article. but I will not spend. I don't want to spend too much time on this here. The second class of structures that is interesting is the positively correlated disordered media. One example, it's a disordered fractal. Here you can see on the pair correlation function that you have some power law scaling where the exponent depends on the fractal dimension of the structure. And you have the same, of course, for the structure factor that depends on this quantity as well. This is, of course, well known, and people have studied fractal aggregates, for instance, and made measured of small angle light scattering to deduce the fractal dimension of a fractal aggregate. This is very classical. What is a little bit less known is that there are many materials that exhibit some multiscale heterogeneity, including also biological tissues. So you can think very truly of cloudy atmospheres, foams, and emulsions. That's an example. That's a serious study that is made on beer foam. And when you have such a strong heterogeneity, actually, you can imagine that the extinction will be composed of rays that go straight through the material, because maybe there will not be any scattering element. And it will go through materials that are strongly scattering. So this heterogeneity makes that the decay of the ballistic intensity will be non-exponential. Okay? And that leads to the main message of this talk. I apologize in advance, which is that Beer's law fails in beer foams. You might want to make the experiment this evening if you want. But this is important. Come on. This process is very important. It has been known again for a long time. People started to study this problem when studying the propagation of neutrons in pebble bed reactors that are strongly heterogeneous. There is a lot of work also on radiation transport in clouds, including a famous work by Davis and Marshak on Levy flights in clouds. And it's becoming important also in computer graphics because people try to represent somehow in virtual scenes the appearance of a cloud, for instance, and this non-exponential decay is extremely important. What I should say is also that the multiple scattering theory that I presented always assumes that you have an exponential decay for the average field, which is clearly not the case in those materials. Some years ago, we studied a little bit the topic, but from the point of view of light transport. Essentially, when you have a homogeneous medium, your light on the intensity will make a kind of random walk that will be described on a large scale by a diffusion equation. So this is actually described more generally by the radiative transfer equation. And when you introduce some large-scale heterogeneities in the system, as I was explaining before, light will make some large step and many small steps in the diffusive material that is between the spheres. And from this, you have a non-exponential distribution for the step length. What was interesting to us at the time was the fact that we could engineer the distribution of the step length in the material. So essentially, when you change the distribution in the size of the spheres, you change the power law that you have in your system. And that allowed us to study an important and interesting aspect of transport, that is superdiffusion. We did quite a lot of theory and experiments also on coherent backscattering in those materials, and had a very nice experimental demonstration of the superdiffusive transport that was measured by time result transmission experiments with a sub-picosecond resolution and a scaling analysis. This paper has been poorly noticed by the community, but it's really a very nice experimental work that I recommend if you're interested. So that brings me to the conclusion. So there are a few messages that I wanted to give. First, I tried to give you an idea of a theoretical framework to describe the impact of structural correlations on light scattering. What is interesting here is that we have a unique theoretical approach to describe the extinction, scattering, and transport of light in correlated disordered media that can be either fluctuating permittivity or particulate media. There has been, in the review article, also rigorous derivation of the expression for particulate media that is beyond the long wavelength approximation, and that was previously established only phenomenologically. And this expression was obtained assuming only that an effective index can be defined. So I think this is an important contribution, I would say, for people who are used to rely on this expression in the experiments, for instance. I should say also there is a generalization of the strong fluctuation theory to anisotropic and chiral media. There's clearly a lot to do, and little is known so far on the impact of higher order correlations on light scattering and transport. So that, in my opinion, is an important and interesting aspect that could be investigated. On the second part, I could say that negative correlations enable strong spectral and angular response that can be exploited to reach exotic transport regimes. We've seen examples of transparency, spectrally selective scattering, localization also, as we have seen yesterday, and create new optical materials for different applications. And positive correlations lead to a non-exponential decay that is often neglected for the ballistic component of the average intensity, and that escapes today the framework of multiple scattering theory. Also, little is known so far on the near-field and mesoscopic phenomena in this kind of media. There are a few works that I'm citing here that are looking at one-dimensional problems, as we have seen, for instance, this morning, and quantities, mesoscopic quantities and phenomena in those systems. You can find out more in our review article that was again written by a great team of people that I want to thank very warmly. As a last slide, some of you, of course, know well Juanjo Sáenz, who left us right in the middle of writing this review article. He was really an exceptional person. I never had actually the occasion to say anything about him in public, so that's why I'm saying it here. Juanjo was also coming quite often to cargèse. He used to sit at the back of the amphitheater and chewing his cigarette all the time and asking all the time really excellent questions. He was known as we might say in French, a bon vivant, right? But he was above all, I think, an excellent scientist, and I think we miss him quite a lot. Thank you.